Okay, so let's continue. So this will just take out the V8 inner product, and then it will be V1, V, V2, V up to Vi minus 1, Vi plus 1. The Vi will miss. This is V, big V, Vn. Okay. This is how the annihilation operator will act on that. How will the creation operator act on? Creation operator acting on A of U, acting on V small. V1, V2, Vn. Okay. This is the symmetrization, which is just symmetric, that symmetrization operator, which is a sum over all permutations of that V1 tensor V2, which is just V1 tensor V2 tensor up to Vn. Then you apply the sigma and then take the sum over everything and divide it by 1 by n. In fact, divided by n in factorial. So it is that. Okay. So a dagger acting on that will be summation of, I mean, it is just the symmetrization. You just attach that U on that and take the symmetrization. I mean, which is precisely V1 tensor summation of n equal to 0 to n, 0 to r equal to 0 to, there will be n plus 1 terms, no? If I take r equal to 0, 0 to n minus 1, let's say V1 tensor U. I mean, you should be, let's just write the symmetrization. Okay, then it doesn't matter. Wherever you put it, it doesn't matter. Okay. You are going to apply the symmetrization operator, which is as U, then V1, V2 up to Vn. Okay. It will permute, it will put U everywhere in the tensor and then submit, and this is what it will do. Okay. See, these are unbounded operators because if you have, it will not see, if you compute the norm of this, okay. I don't know whether I'm missing some n factorial somewhere, but up to a constant, it is like this. Okay.
Should we put a bracket on like V1 up to V?
Why do we need a bracket?
Oh no, sorry.
There is no bracket. Okay. There is no need for bracket.
Yeah.
It is just a symmetrization of U tensor V1 tensor V2 up to Vn. We just symmetrize the whole thing, sum and everything. I am just worried whether there will be a constant n or divided by, possibly divided by 1 plus n plus 1 power half or something, some TC times this. Okay, I mean, you do the computation, it's part of your work, but the thing is, it's constant times this. Here also there may be a constant, I don't know. That constant will depend on n. Eh? No, it will be a square root somewhere. Because there you get a square root, no? Here also it will be a square root. See, if you just compute the assignment wherever I wrote, you will get a square root somewhere. Now here there is no, here it's only symmetrization. So possibly there is no, for the dagger, there is no n, there is no constant. For annihilation operator, there may be n. Square root, I don't know. So if you do the computation, it will be clear. Okay. Okay. So what we have is the following. We have this, I mean, we have that, we have A of U, T A of U xi equal to A of U T xi for all xi in finite particle vector space. And similarly, T A dagger U xi equal to A of U T xi for all xi in finite particle vector space. Okay.
Using
Yeah, I mean, we have this relation on exponential vectors. You get that V tensor n as limit of exponential vectors, so that is in the thing. Then by linear taking combination and other limit, you get this, so it will satisfy this for all finite particle vectors. Okay. Once we do this, now it's clear. Now what do we have to do? First thing is, let us first T phi, you take T phi and take its. So what is any finite particle vector is? Any finite particle vector will look like A dagger U1, A dagger U2, up to A dagger Un of phi. If you apply A dagger Un on phi, it will go to Un. first particle vector space. Phi is the zero particle vector, okay, vacuum vector. When you apply A of un on the vacuum vector, it's a creation operator. It will go to the first particle vector. Then if you apply A of un minus 1 or A of whatever, another creation operator, it will go to the two particle vector space. Okay. If you vary all u1, u2, you will get all vectors, all two particle vectors. So similarly, so any finite particle vector will look like this. Okay. Okay. Now this is equal to, because it satisfies the adjoint relation. So this is going to be A dagger un up to A, sorry, A. Here it's just A. Up to A of u1 T phi acting on phi. Right? But then T commutes with all annihilation operators on phi at least. We are only worried about that. We don't even need that. We are worried about on phi, which is E of 0. Here A commutes with that. So this is just T of A of u1 to A of u1 phi. But this is equal to 0. Okay. Because its annihilation operator acting on vacuum vector is 0 because of that. So these things implies T phi, which is a vector, is orthogonal to all finite particle vectors. All n particle vectors for n is, I mean, it's orthogonal to all n particle vectors for n greater than or equal to 1. So this implies T phi equal to some lambda times phi. Okay. T phi equal to lambda times phi. Okay. Now, T acting on any finite particle vectors. T acting on any finite particle vectors. A dagger u1 up to A dagger un. Okay. That is equal to, but then you can take the finite particle vectors outside, no? So which is equal to, it commutes with that. So A dagger u1 up to A dagger un of T phi. But T phi is lambda phi. Okay. So you get a lambda phi there. So you get lambda of A dagger u1 to A dagger un of phi. So T acting on any finite particle vectors. So this implies T acting on any xi equal to lambda xi for all xi in finite particle vectors. But finite particle vectors are total. So this implies T equal to lambda times 1. That's what we want to prove. Okay. That's what we wanted to prove. I was bit sloppy where annihilation operators and other things. Okay. Except that, but if you want a real probabilistic proof, look at KRP's book. He gives a completely different proof. He does not use all this A and A dagger and other. I'm just saying, so the fact I'm using is T commutes with creation and T commutes with P of U on finite particle vectors. Okay. Then any finite particle vectors is, you get it by applying the creation operators on the vacuum vector. Okay. There it commutes, so it's because of that this is true. Okay. Okay. So I stop here today.